Our design process started with the design and construction of our frame that we're going to use to hold our solenoid. First, we began thinking that we were going to 3D print a frame. However, after considering some of the structural compromises that we would have to make in order to successfully 3D print the frame that we had in mind, we decided that 3D printing was not going to be the way to go. Upon realizing this, we went from 3D printing to a welded design. One of our group members welded two 1-inch pipes at a 45-degree angle in order to create an arm of sorts. This was structurally sound, however, we had trouble stabilizing it due to the nature that it would rock back and forth, which created a problem with our KP and KD values when we were trying to be so precise. Following the abandonment of this, we went on to build a more simplistic wooden frame, which basically resembles a vertically standing rectangle where the top horizontal board has a 3/4 inch hole drilled in it to fit our 5/8 bolt that we ran through the solenoid. Later, we added a couple of additions, including feet at the bottom of the rectangle to aid with stability, along with a second, or rather third, horizontal member running across the middle of the rectangle to add just a shelf in order for us to sit our sensor on.
For our magnetic levitator, we needed an object to levitate, and our first go at it was a bolt that was about 1/4 inch in diameter and 1 inch long, but that proved to be too heavy, which meant that we had to crank up the solenoid in order to get it to stick, but then it would just stick to the solenoid, and if we turned it down even a little bit, it would just drop because it was so heavy, and that's not good for levitation. So our second try was a magnetic dart, which we glued a nut to the other end to, the fin side, so it'd be opposite of the magnet. And the problem with that was that, well, one, we weren't sure if it was strong enough, so we glued another magnet to that bolt, to that nut, but it had balance issues, so the dart would levitate for a couple milliseconds or something, but then it would tilt to the right, and then it would be that much closer to the solenoid and just stick to it. So for our third attempt, we have a ping pong ball with a screw screwed in one side and a magnet glued to the other, and it's round, so we don't have those tilting issues, and they're more or less equally balanced, the screw and the magnet, so that helps.
Now we will discuss the design of our sensor. For our sensor, we chose the Hall effect sensor, which is a transducer that varies its output voltage in response to a magnetic field. In order to use it to measure the distance from our electromagnet to the object, the levitating object has to have a small magnet on top for the sensor to pick up on. It measures the distance from the sensor in the direction normal to either of the sensor's two big faces. It then generates a voltage signal in response to this distance measurement that is then sent through the rest of the feedback loop to the controller. Our original setup was with the sensor being mounted roughly 3 millimeters below the bottom of the electromagnet. But due to the electromagnetic field generated from our electromagnet, it was interfering with our sensor and causing it to saturate. One typical solution that we considered was to use two Hall sensors, one to be mounted on top of the electromagnet and one to be mounted at the bottom, both of them reading the distance of the distance of the levitated object. But due to the height of our electromagnet, the sensor on top was not able to gain an accurate reading, so this method was not viable for us. So the solution we came up with was to essentially reverse the setup of our original idea, such that the sensor would be placed below the levitated object and the magnet on the levitated object would be on the bottom, such that when the levitated object gets closer to the sensor, it means it's farther away from the electromagnet, which then the controller increases the current in the magnet, which increases the electromagnetic force pulling the object back up. And once the sensor reads it being farther away, then it realizes that it's closer to the electromagnet, so it then corrects by reducing the current in the electromagnet and allowing the object to settle down and move farther away from the electromagnet. And this concludes the discussion of our sensor design.
Hi, this is Scott Malone, working on our Levitator project, and we have it set up here in the lab, so I'm just going to do a little bit of explaining on what we have going on here. And that's Brad over there with our setup. This is our little levitating dart, as you can see. And so we have the oscilloscope that's measuring our pulse width for our pulse width modulation, which is coming out of our Arduino. And then the Arduino is controlling our MOSFET that we have here. And I also have this meter set up so that we can read the sensor voltage while we try to float the dart. And as you can see, we can get a little bit of wiggle, but we have not yet been successful in getting the project to levitate our object. We think there's several different possible factors that could be influencing that, between just incorrect settings for our gains, a little bit of hardware issues, but overall I think it's been a pretty good approach, and I think the team has learned a lot on how feedback systems work.
It's time to try defying gravity. I think I'll try defying gravity, and you can pull me down. I'm through accepting limits, 'cause someone says they're so. Some things I cannot change, but till